So in the last class, we saw how using various Boolean algebra we can simplify Boolean expressions, right? We learned a few Boolean laws and postulates. Using that, we can simplify the Boolean expression, right? So now there is today we are going to learn something known as KMaps or Carnot maps. Okay. Now why do we and what is the necessity of using KMap, since we have already learnt about an algebraic simplification? Okay, the reason is algebraic method lacks specific rules, right? So say there is a big expression which requires to be simplified. It is possible that Saksham use one set of rules and he will get one answer which may not be the optimum, and Kishan might use some other set of rules and simplification postulates, and he might get a result which is much simpler and you can be implemented with lesser number of gates. So algebraic method lacks specific rules. It is more dependent on human beings. Okay, so we need something which is more systematic. So we know truth tables, right? So for any function we can make a truth table. Okay, but from truth table again, if you go back to algebraic expressions, we will find we can combine all the min terms, but that is not an optimized solution. So truth table is the starting point but not an end point. Then complexity of implementation related. So some expressions might be very complex in nature. There could be 4 variables and then what rule to apply, and so it may not be that simple for us to decide. Okay, so KMaps provides a simple method, straightforward method, pictorial understanding. Okay, again let me just clear one aspect here itself. This KMap is also intended for human beings. Like the computer doesn't use KMap to simplify the expressions. Okay, computer uses a different method which is known as QM method, which we will learn next week. Okay, this KMap is again a method which you and me can use, okay, using a pen and paper. Okay, so the KMap is used as a simple method, and that is why it is written pictorial understanding. Okay, so it gives human beings a good understanding of how to solve these Boolean expressions, to minimize the Boolean expressions. Okay, so the first we will take a 2 variable KMaps. Okay, what is 2 variables? There are 2 variables and you have an function f. So the function f, like you have for 0 0 the output should be 1. So this is known as the truth table. So this is the truth table. From truth table, how to make KMap. Okay, so each of them we know they are this is min term 0, 0 0 is min term 0, 0 1 is min term 1, this is min term 2 and min term 3. This we learnt again in the last class. Okay, now if you have to map these min terms onto the table, okay, this is how we are going to write. Rows, this particular row represents 0, and this x is equal to 0, and this particular row represents x is equal to 1. This column, okay, represents y is equal to 0, and this column represents y equal to 1. So in all we get 4 different boxes. So each of them will represent one min term. So this is going to be 0 0. So this is going to be min term 0, and this is 0 1, min term 1. This is 1 0, so it becomes min term 2. And this is min term 3. So you all the min terms have got a unique position in this table. Okay, so you write x is equal to 0 and y is equal to 0. Here generally we write this as MSB and this as an LSB XY. Okay, you can write it the other way around also. There is no issue. But only thing is when we are making an expression, we got to be careful. Okay, we just have to remember that this row represents x is equal to 0, this row represents x is equal to 1, and the vertical columns represents y is equal to 0 and y equal to 1. So now the next thing which we need to do is from the truth table we need to map these functions into the truth table. So here we find for x is equal to 0, y is equal to 0, output has to be 1. So we map that 1 into this box. Okay, then again for the next min term it is 0, so we map that 0 here. Okay, The third is again min term 2, so we are going to map it 0, and the fourth is 1, so we map it to 0. So this is the first step towards solving an function, minimizing a expression from two table using KMaps. First we need to make an KMap table and put these value of the functions in the corresponding table here in the KMap table. This is known as a KMap table. Okay, we put these expressions out here. Now what next? Okay, now representation of the cells, again like I said, this is actually M0. So it is actually x dash y dash, right? This also we learnt in the last class. M0 is 0 0, that means x dash y dash. Okay, why we are talking about this also here is finally how to implement the hardware. Okay, so we need to know these also. So this is an x bar and y, because x is here, if you see, this is 0. A 0 column, 0 row for x, right? So this becomes x bar, and this is 1 for y. Y is 1 here. So you have this y x bar and a y. So these are the 4 expressions and min terms corresponding to each of these cells in the KMap. Now if you see one more particular property of this KMap is, when you are moving from here to here, only one variable is changing, right? If you have, this is 0, this is 0, this 0 is changing from 0 to 1. And if I am moving from here to here also, if you find this 1 and 1 is remaining constant, only this 0 and 1 is changing. From here to here, again you will find, when you are moving from this cell to this cell, you will find this 1 remains same, 1 is changing from 1 to 0, and from bottom to top also, when you go from here to here, also you will find 1 0 is there, 1 2 0. So this is a very important property of the KMap, that two adjacent cells will have only a variation in one of the parameters. Okay, both the terms will not have a change. Okay, so there is, if you see these all the 4 of them, they're changing only. You can't take you can't do an diagonal in the diagonal boxes. You will find there are variation of two elements, right? So diagonal we will not be considering. Now only in the, we'll either move in the x direction or in the y directions. The two cells will have only one parameter varying from each other. Okay, so what is the importance of 1 bit variation? Okay, so the importance is, if you see here, now we are going to map these. This function has been mapped here. Now what is this element? Okay, this is x dash y dash. Okay, this is the min term corresponding to. What is this element? This is x dash y. Okay, now I have to if I have to write a function f from truth table, I can I'm just talking about only these two functions right now. Okay, these are 2 are 0, so these 2 are 1, so I can write an x dash y dash plus x dash y, right? If I take x dash common, okay, from these two expressions, it becomes y dash plus y, which is 1, so I get x dash here. Okay, so this actually these two, okay, you can, if I write the min terms and if I do an algebraic summation, I get x dash. Okay, now seeing this table also, I can say that it is x dash, because there are 2 ones out here. If I club these 2 ones together, if you see, let me put it in the next slide, so it will become, now here I can club these 2 together out here. Now if you see here, what is constant in these 2 terms, in these 2 cells? X dash. Okay, y is changing, so whatever is changing, y is changing 0 to 1, so we leave that. What is remaining constant is x, and what is that value of x? It is x bar, because it is 0 here, right? So directly seeing these 2 ones, I can write this corresponds to, this function corresponds to x bar. Okay, so is this clear to all of you? Yeah, Kishan, Sachin, anybody? Because everything starts from here. If this is clear, then we can build our concepts for 3 variables, 4 variables. How seeing this box, we got x. Okay, great. Okay, So now keep writing in the chat box so that I know I am not going fast. Okay. So this is how. So we now you got a small taste of how we can simplify the function by writing it in a truth table. We'll take few more examples, then it will become fully clear. Okay. Now if suppose this is another function where I have 1 here and a 1 here. Okay, that means for 1 0 and 1 1 it is 1 here. So in the truth table this one is available here, this one is available here. Okay, just seeing the truth table, can anybody make a guess what would be the function? Anybody can just make a wild guess. Doesn't matter even if it is wrong. Any one of you, right? And what is going to be static in these two? We are going to, because these are adjacent cells, we are going to club these two together, right? So if we club these two, y is changing, so we don't talk about y. X is remaining constant, and this time it is x is equal to 1 is gone. So the expression for this would be simply x. Okay, so this is how we can simplify this. So this function corresponding, we can write f is equal to x. If you see here also, x is 0, output is 0, x is 0, output is 0, x is 1, output is 1, x is 1, output is 1, right? So you can simply write f is equal to x from the truth table also, and that is what we get in the KMap also, right? So here we see that straight away seeing here also you can write, but when we see 3 variables, 4 variables, but just by seeing the truth table you will not be able to simplify, but we can use the KMap to get a simplified expression. Okay. Now we take one more example. Here if you see here, we have got all ones out here. Okay, that means irrespective of input output combinations, the f remains 1. So you have 4. So it is possible that okay, we make one box out here and the second box here. Now this corresponds to x and this corresponds to y, and then we can write x bar plus x, which is nothing but 1 out here, right? So rather than making two boxes, KMaps permit us to make a single box also of 4. Okay, you can't make a box of 3. Okay, remember that. We can only make square boxes. Obviously in 2 by 2 there is a possibility of only making a square box with either we can make a box of 2 or 4, but for 3 by, when we go higher one, then we will see that we have to make 4. We can't make a box like 3 box. Okay, 3 elements. It has to be 2 or it will be 4 in the 2 variable k box. So if you see here, here we said only elements which remain constant we take into into the expression. Here in these 4, even x is changing and y is changing. Okay, that is why we straight away write it as 1. Okay, so that is how we can do that. Okay, we'll take more examples out here. Now this is one more example where you have 0 0, you have 1 out here, 0 1 is 0, and 1 0 is 1 and 1 1 is 1. Okay, now we need to find an expression for this. So if you see here, we can make one box out here like this. And the expression for that will be x. Okay, because y is changing here and x is remaining constant as 1. So the expression related to this box is x. And we can also make an vertical box like this out here, right? And then you will find 1 and 1. So that corresponds to y equal to 0, or you can write it as y bar. Okay, so it will become f is equal to x plus y bar. Okay, now let me tell you something. If there is only one, which there is a single one, then for this particular single one, I can write it as x bar plus y bar also. Okay, that is the expression corresponding to the min bar. So in certain big tables, it is possible that you don't have an adjacent cell. You suppose it is a 0 here also, then this becomes a single element. Okay, in that case also, here if you see here, although it was an single element, this one was already covered by this box. Still, instead of taking this remaining one, we made a bigger box. So in KMaps, we have to always target the biggest possible box for each element, even if it means there is a repetition of one element here. Now if you see here, this is getting repeated in this box, doesn't matter. Okay, still, because this, if you take this as a single one, then it is better to have a double box, because single one will have a bigger expression, x dash plus y dash, whereas this will have a y dash. Okay, if you write x dash plus y dash, x plus x dash plus y dash, it will unnecessarily generate one more gate, right? So you have to, we can do these kind of clubbings. Is it clear? Yeah, Ritika, is it okay? Okay, now we have just till now we have seen two variable KMaps. Now let's take an example. What if we have three variables? Now if you see here, we have written 0 1 out here, right? This row represents 0 and this row represents 1, whereas on the columns there are 4 columns, because now there are total of 3 variables. So one variable we have taken here. Now we are going to take two variable here. With these two variables, there is going to be 4 different combinations possible, right? So how to write those 4 different? So first one will be 0 0. Okay, next one will be 0 1. So this first represents an x 0. Okay, x is equal to 0, y 0, y 0, x 0, and then z1. Now the third one, what should be? Now see, for us to simplify, right, if we write 1 0 next, okay, what happens is, while we cannot club these two cells in that case, if you write 1 0 excuse me, because if you write 1 0 here, this 0 has to change to 1, then 1 has to change to 0. So there will be 2 changes as we move from here to here. There will be 2 changes. So we have to write in the form of a gray code, so that when we move from one box to other, there is only one change. So the next what we are going to write out here is 0 1 1, and then we are going to write 1 1 0 here, right? And then here we are going to write 1 1 0, 1 1 1, 1 0 1, and 1 0 0. Now let me write the min terms out here. Okay, now if you see here, okay, this is m0, m1, then m2, and then m3 here. Now if you see, from when I'm moving from here to here, only one bit variable, right? From here to here, again there is only one bit which is changing, that is the middle one. From here to here, again the last bit is changing, right? And from top to bottom also, if you come here, okay, 0 0, this the MSB is changing. From here to here, again only the MSB is changing. Here MSB is changing, MSB is changing. From here to here also the MSB is changing. If you see here, we have written it in such a manner: 0 0, 0 1, 1 1, and 1 0. By writing, so what have we achieved? We have ensured that two boxes have got only one variable. Okay, one element which is varying when we are moving from this box to this box. Okay, is it clear now how we got this box? So this is very important way. If you are going to write 1 0 and 1 1 here, this entire system, our logic fails. Okay, so we have to ensure that the way we are writing these 3 variable KMaps, it is in written in this manner. Okay, 0 0 0, 0 0 1, 1 1, and then 1 0. Okay, so this 1 0 and 1 1 places have been interchanged. Okay, so that is how we write that. Now if I write in terms of min terms, this is m0, m1, okay, then m3 instead of m2. Now we are writing m3, then we are writing m2. Okay, and then we are coming to m4, m5, and then m7, and then m6. Okay, we have to make sure that only one bit will change. Yes, Kishan, we have to ensure that only one. So it is like, this is a standard. Okay, you don't have to remember that. We need to just follow the gray code. Okay, 0 0, 0 1, 1 1, and 1 0. Okay, so this pattern we need to remember. Okay, so this is going to be constant. Now for every function, this doesn't change. The format of the table doesn't change. For 3 variable, this is the standard format which we will use. Okay, only the values of the function here, wherever we need to put 1, that changes. Okay, so this is the standard way of writing a table. Okay, this won't change. This is constant. So you don't have to really remember this table. This should come naturally to you. 0 0 0 1 1 1 and 1 0. This is known as gray code, right? And 0 1. So this have to be run. Okay, once that is done, let's try and see what happens. If these two adjacent cells, again you will find 0 to 1, only 1 change. From here to here, again you will find only 1 change. Here to here, again 1 change. Here to here, there is only 1 change. Here to again you will find 1 change. Single change, single change, and single change. Okay, so this is important. So this is the reason why we are writing in this particular pattern. Okay, now also if you see these two columns or these two boxes also, so if you will find from here to here also there is only 1 change, 0 0 0 and 0 1 0, right? So there is only 1 change. So you can club this leftmost and the rightmost columns also. Similarly in the bottom also, from here to here there is only 1 change. This is 1 0 0 and this is 1 1 0. So you will find these two also, these corner boxes also can be clubbed to form a box of 2. Okay, so that is also a possible combination. Okay, so if you take few examples, then things will be more clear. So I have 0 out here for this 0, and I have one more 0 and the third minterm. Now if you see, it is 0 1 0. Okay, the third minterm, this 0 has to come here. Okay, not here. Okay, so with a few practice, this will come automatically to you. First 0 0, and then the third one is going to the rightmost position, and then 1 is going to come here. Okay, so this position is interchange. Similarly, I have 1 0 coming here, and next one is coming here. The next one is going to the outermost cell, and then the final one is going to come here. Okay, so this is the first step. And once we write this truth table in this particular gray code format, then we put all the 1s and 0s corresponding to this function in the table. Okay, and now the next step is how to group them, right? So now you have to group them. So this is one way we can group these two. These are two adjacents. Okay, now the expression, okay, now this is the second grouping which we can do, and instead of again I said leaving this alone, it is better we form an two loop is possible, group with 2 elements is possible out here. So even if this is a repetition, okay, I make a group like this. Okay, so this one is getting repeated n number of times, doesn't matter. Okay, so I have now 3 groups here, and if I try to write the expression each, now if I take first one for the blue one, you will see x is varying, whereas y and z are remaining constant. Okay, and y is 1, z is 1, so I can call that as yz. Okay, similarly if I talk about this, in this case it is, if you see from here to here, x is remaining constant 1, right? And then also this is 0 and 1, y is changing, z is not changing, it is remaining 1. Between these two, I am talking about the red one, so this becomes an xz. Now in the third one, if you see here, now if you see x is remaining 1, right, in these two terms, and y is 1, whereas z is changing. So whatever is changing, we leave that. What is remaining constant, we pick that. So y is 1, x is and y is 1 and x is 1, so that expression comes to be xy. So the final expression we can write it as an xy plus yz plus xz. Okay, so this is the simplified expression for this truth table. So is it clear to all of you? Yeah, Saksham, now is it clear how to make an 3 variable to table? Okay, good. So Now let's take one more example out here. Now here f of is defined as f is a function of variable x, y, z, and the min term 0, 2, 4, 5, 6 is given out here. So first we make an truth table. So you need not make this truth table also. If something like this is given, you can straight away, because we know the boxes corresponding to the min terms, right? This is 0. 1 is not mentioned here, so this becomes an 0 out here. Again 2 is mentioned here. This is 2, this is 3. Okay, you got to remember that m2 3 is here, and this is here. Okay, so we need to put an 0 out here, and then we have an 1 coming here. This is because a min term 4, this is a min term 5, and then 6 is going to come here, and 7 is going to come here, right? So 6 is there, it is 1, and 7 is 0 out here. Okay, so now you have a 1 1 out here and a 1 here. So now so this truth table you need not make, right? So if the function is given here, we should know how the min terms are placed: m0, m1, m2, m3, m4, m5, m6, m7. Okay, so that is the order in which the min terms are placed in this table. So accordingly we can now the first, once you make this, now it is up to us to make the boxes out here, right? Now if you see here, one box can be made like this here, okay, because this is 1. So this comes to as, now if you see here, x is not changing here between these two, so x, and then you will see y is not changing, y is remaining 0 here, and y is remaining 0 here, z is changing 0 and 1, so it is x dash, y dash. Now remember this, okay, now because y is not changing and it is 0, and that is the reason we are writing y dash. Here also x is not changing, but it is x is 1 out here, so that this row corresponds to x is equal to 1, whereas these two columns corresponds to y is equal to 0. So that is why x and y dash, we write this x as y dash. Okay, now there are 1 2 3 4 ones. Instead of making two boxes, and we can make a 4 box also, right? We can make a 4 box, and also that is also possible. So we are making a 4 box like this. Okay, now we can't make a box out of this column and this column. Okay, we said between the outer columns also, now they have only single variation, like it is 1 0 and 0 0, so only one element is changing. But if you see this column and this column, if you see 1 1 and 0 0, so you can't have these two being combined. So only combination what we can have is, if we are outermost, like in this case, these 4 can be combined together. Okay, now if you see these two combined, you will find x is changing, and also this z is changing, right? No, z is remaining constant here, 0. Y is changing, so z is 0 here and z is 0 here. So I can straight away write that this 4 box corresponds to z dash. Now a few things we should always remember: when I am clubbing two elements in a 3 variable KMap, I will get an expression of containing 2 variables. If I am having a box with 4, it will have only single variable. Okay, now these 4, if you see, it is corresponding to z dash. Is it clear? Yeah, Kishan, have you understood how we got this expression? Right? Yeah, Mariam, are you able to follow? You just missed out the initial portion, so I understand there will be a bit of problem. But others, okay. So let's take one more example. So now the min terms are given as 2 3 4 5, right? Okay, now let's see how to write. This is m0, we know that min term 0, this is min term 1, min term 2 will come in the end, so I put a 1 there. Min term 3 is also there, so I put one more 1 here. Then I put one min term here, okay, this corresponding to 4, and then 5, and then 5 is 0 here, and 6 is 0 here, right? So I have 4. So if you see here, I can make straight away, I can say I can make only 2 boxes. So I make one box here and I make the other box here. Now for this, if you say if x is a constant here 1, and also y is changing, no, y is continuing to remain 0 here. It is 0 0 and 0 1, so y is 0, so it becomes x y dash. Whereas so this expression is x y dash, and if you see here it is x is remaining constant, so it is x dash, and you will say y is constant, z is changing, so it is y dash. Now since these are both are of two variable boxes, and that is why you have two variables here. Had there been a bigger box, then it of 4, then only one expression will be there. Here you will find there are two boxes, each of only 2 elements, so that is why this expression comes like this. Okay, so this is nothing but an XOR gate. No, sorry. Yeah, it is an XOR between an x and y. Okay. Now let's take one more example. Now you have 3, 4, 6, and 7. These are the minterms. I am showing this table, okay, just to further amplify this aspect. But then for your exam, you don't have to make this table, right? If this is given straight away, you can make an KMap here. We know where to place. So this is M0 is 0, M1 is 0, M2 here in the corner is 0, and then come M3, which is 1, and this is going to be 1. M4, M5 is 0, M6 and M7, M6 and M7 is going to be 1 1 out here. All right. So if you see here now in this table, how best we can make the number of squares. Okay, this is 1 square. Okay, this is 1 square. Now there are 1 out available here, 1 out available here, right? So and these two also can be combined, right? So we can make it in a simply like this, right? These outermost also can be combined. So we and this also can be done here in this particular case, but this is redundant actually, so we should not be doing that. Okay, so is it necessary? No, because these minterms, this particular 2 elements have already been covered, right? So every minterm has to be covered once. Okay, so obviously, like in the previous case, if I go back here, yeah. Here this one was covered twice. Okay, that is okay, because we wanted to make a bigger box. That is okay. But in this case, in this particular case, coming back to this, now here this one has already been covered by the red box, and this one has been covered by the black box, right? So now since all has been covered, there is no necessity to make one more box here. Okay, so so we have to make boxes in such a manner that all the minterms have been covered at least once, and with the biggest possible box. Okay, now these are the 2 important things which we need to remember. One, every one has to be covered at least once, and then by the biggest possible box. Okay, so obviously these ones are covered at least once by this red and green, so the blue is redundant. Okay, so we need not do that. So if I write the expression for this, if you see here, this is x is changing here for the red one, so it is y and z, so y z, and if I take these 2 here, if you see, it is x is 1, and whereas y is 0 here, y is 1 here, so z is 0 here, z is 0, so z bar. So I write this black one, which is x z bar. I don't take this blue box into consideration in this particular case. Okay, so if I write an expression for that, it will come as an xz. Okay, if I write that. Okay, now if you simplify this, if you see here, and if you try to simplify this, then you will reach the same answer out here if you do algebraic simplification of this. Okay, so that is the reason we don't write it like this. We unnecessarily increase the number of gates out here. Okay. So let's take one more example. Okay, in this case we are now talking about max terms. Okay, so if you say, it says 2, 3, 4, 5 max terms. Okay, now so that means m okay, for right, so you will have 2, 3, 4, 5. So 2, 3 and 4, 5. So these are where we have this is the function which is given here. So it is 0 for 2, 3 and 4, 5 we have 1 out here. Now if you have to implement using collating these zeros, we can do even collate the zeros also. Now the only thing is when we write the expression, okay, what would have been these expressions had it been a 1 1, we would have written it as an x bar and y bar, okay. But if you are collating zeros out here and putting a box out here, we need to write it as x plus y, okay. And similarly if you go out here, okay, it is, if you write here, it will be we would have written normally x plus y here, but we are going to, for this red, when we are writing in terms of max terms, we are going to write as x bar plus y bar, okay. So if the question says, if we have, so this is what implementation of an OR gate, implementation of an OR gate and then putting an AND gate, okay. This is like product of sum, and though initially we were doing sum of products. So when you are doing a product of sums from the truth table, wherever there are zeros, we are going to club that, and then we are going to write the expression in this manner, okay. This corresponds to x plus y, okay, and this corresponds to x bar plus y bar, okay. So easy way to remember is, if you see what is changing here, right, it is x is remaining constant, x0. So and then here z is changing, so it is x bar y bar in terms of AND gate. So if I have to invert it, because if had it been 1 1, I would have written an x bar y bar. Since it is 0 0, I have to invert it, right? So x bar y bar, the whole bar will be x plus y. That is De Morgan's theorem. So that is how I write this expression. So is this thing clear? Is it confusing, or should I repeat this aspect? Is it clear, Kishan? Anybody? Can you just give a hint? We will proceed further. Yeah, okay. So let's take one more example out here. Now this expression has been given here, right? And a dash c, a dash bc, bc. So from seeing this expression also, we can write these min terms of out here, right? So a dash c, right, a b c. So these min terms corresponding to these expressions have been written. Actually if you see here, when we write, we have to expand this. A dash c is actually you have to write a b plus b dash, right? And then if you expand it, you will get an actually 2 ones there. Similarly this is 1 1 here, there is 1 here. So if you expand this expression in terms of this, we learnt in the last class, right, how to expand this. We have to write b plus b dash here, so it will become a dash c b plus a dash c b dash, right? Similarly here we have to multiply it with a plus a dash, so it will become an abc and a dash bc. So you will find, if you see here, this is going to give me 2 terms, this is going to give me 2 terms, 6 7 8. So there are 8 ones out here, right? Is this thing clear, how to write these expressions, how to get these values out here, right? So where to find a dash c here? Okay, a dash c is nothing but a dash b. You have to multiply with b, a dash c into b plus b dash, okay. So that will become, give 2 terms, a dash b dash c. A dash b dash c is what? 0 0 1. So 0, this is 0 0 0 0 0 1. So I put that one here. Similarly this will give a dash b dash, a dash bc also. So that will be a dash and bc. So I put a 1 here. Now this is a b dash c, so that is 1 0 1, okay, 1 0 1. So I put a 1 here. This is bc. Now bc also cannot be written straight away. I have to multiply it with a plus a dash. So I will get an a dash bc first. So a dash bc is what? 0 1 1. So 0 1 1, I put a 1 here. Again I multiply this with an abc. This will also give me abc. So abc is an abc is here, okay, here, right? A b c 1 1. So I put an a 1 out here, right? And then similarly this is an a b dash c. So you got to multiply it with c plus c dash, and this is final a dash b. So if you see here, this is going to give me 2 terms. This is going to be 1. 2 3, 3 plus 2 again, and 5, 5 plus 2 7 plus 1 8. So 8 ones have come here, right? Is it clear to all of you? I hope so. Okay, now once this expression we have this KMap here. Now 4 box is possible, so I put this one full 4 box, and then this one will be left out here. Now I said where possible, if it is possible to make a bigger box, then we should make a bigger box, even if it is overlapping other box, doesn't matter, because if I write only one, then it will give me a 3 variable expression. If I if I put only one this box, this expression for this one, if I make a single box here, it will be a dash b c dash. But if I make an blue box like this, it will be a dash and a dash b, because c is changing. So a dash b, and corresponding to this green box, I will have a and I see b is 0, c is changing. So a b, it is an a b dash. So this is a b dash, this is a dash b here. Now I have these 4 elements can be again clubbed into a single box. And what is this single box? A is changing here, and here also b is changing. C is remaining constant as 1. So that becomes mere c. So since it is an 4 box with an 4, so only one variable is available here, whereas this is an box with only 2 elements. So there are 2 elements out here, right? Okay. Now for an 4 variable KMap, which we will learn shortly, in that a 4 element box will have 2 and 2 element box will have 3 variables. Okay, so this is not an universal, this is specific to 3 variable map, where a 2 element 2 boxes means 1 variable is out. Okay, if you take it that way, then out of the 3, 1 goes, 2 remains. When I make an 4, then obviously 2 variables are out now. So out of the 3, 2 are out, only 1 remains out here. Okay, so you can remember it that way also. So this is one more example out here. So let's take a few more example. Now you have 0 0 1 0 and 1 0 1 1, right? Now if you see here, if I have to combine all the zeros and make an box, then I can combine these 2 zeros and I can combine these 2 zeros. Now the expression for these 2 would be here x is changing, it is y dash z. So if I take in complement of that, this will become y plus z dash, and similarly in these 2, x is 0 and then if you see here to here, y is changing. So x dash, it is x dash into z dash. So if I take a complement, it will become x plus z. Okay, so now if you see here, the total expression is y dash plus z bar and x plus z. Okay, so this is how we can either club the zeros. Okay, so hardware wise, you will require 2 OR gates and 1 AND gate here. If you club the ones, you will get an AND gates and followed by an OR gate in between, right? So 2 ways of implementing the same thing. So by clubbing the ones, we make a sum of products, and we use AND gates followed by an OR gate. When we take zeros, then in that case we make a product of sums, and then hardware wise we will use OR gates and followed by an AND gate. Okay, so that is how we are going to do. Now there are certain something known as don't care conditions. Now this is one particular function. Okay, and now it has got 2 1s here and 2 1s here, so we make an expression. You get f is equal to bc plus ac dash. Okay, this is fine. Now for okay, now if you find here for 101, the output is 0. This was specified earlier, so that is how we got that expression. Say for some reason we are not bothered about now what will be the output here. Okay, that is because we don't expect this input combination at all in our circuit. Okay, what is this finally? We are taking A, B, C, right, and then we are making some input combinations, and for it we don't expect this combination at all coming at all. Okay, 1 0 1. Okay, If that be the case, then we can simplify this table even further, okay, because this expression is not going to come at all. So instead of restricting it to 0, right, I am going to put it as x. Okay, now because this is known as a don't care. Don't care means please don't bother about that, you can use the way you want it. This input combination is not likely to come into your circuit. Okay, this is, it could be from sensors, or it could be because of result of some arithmetic computation for some reason. I'll give you some practical examples also after this. Okay, for some reason this particular input combination is not likely to come at all, so I will call that as don't care. Now instead of putting a 0 here, I put an x here. Okay, the advantage of putting it x is I can take it either as 1 or 0. It is up to you for your own advantage to simplify the expression. Now in this case, if I take it as 1, you will find I can make a big 4 element box, right? So I will take that as a full box, and then this becomes an BC, whereas this full box becomes A. So I get an earlier expression, and without this being taken as a don't care, it was BC plus A dash. Now you find this expression has got simplified. Is it clear to all of you? Yeah. Okay. So this is known as don't care. Now let me tell you. Don't remember the circuit and all. Let me just tell you. This is an A to D converter. Okay, now what we do is generally we give an analog input. If the analog last part, sir, okay, this is like if it is a don't care condition, then we can club it to our advantage. We can either write 1 there or 0 there. In this particular example, if you take the value of x is equal to 1, then I can combine this 4 into a bigger box. Instead of taking 2 boxes, one here, if I put 1 here, I can make a single box. If I put a single box, my expression simplifies. Is it okay, Sachin? Sachin, is it okay? Is it understood? Right, whenever there is an don't care, then we can use it to our advantage, whether we can want it to use it as 1 or a 0. Okay, so I'll give you more examples on this also. So that now this is okay, an A to D converter. Okay, where you give an analog input, you are giving the same analog input to 3 comparators. Okay, so this comparator will check, and if the analog signal is more than this, you will get a 1 here, and if the signal is slightly more, you will get 1 here, 1 here, and if the signal is again still higher, this because say you are giving 1/4 of the voltage into this negative terminal, again 2/4 of the total voltage to the negative of this comparator, and 3/4 to this negative. Okay, now if you find here, now the analog signal, if the analog signal is close to 0, all the comparator will give an output of 0 0 0. Okay, now as the analog signal keeps going high, this comparator, okay, this as the voltage increases beyond 1/4 of this voltage, this comparator will give me a 1, and again slowly the signal will go high, then this will give me a 1, again the signal will go high, this will give 1. Okay, now in this case, can it happen this is 1, this is 0? It can't happen, right, because it is the same signal. So only after this is 1, this will become 1, and after this is 1, this will come 1. So if you see what are the possible outputs from these amplifier, either it can be 0 0 0, or it could be 1 0 0, or it could be 1 1 0, or it could be 1 1 1. That means from the output of the comparator, there are only 4 possible outcomes. Okay, it can be 0, or all zeros, or 1 0 0, 1 1 0, 1 1 1, right? Whereas this is a 3 variable output. So out of the 3 variable, out of the 8 possible combination outputs of 3 variables, only 4 is what is possible here. Okay, so we can, when we are designing a circuit out here, we can consider rest of the 4 as don't care, because they are not likely to come at all for this particular circuit. So you understand where did this concept of don't care came in. Okay, don't remember this circuit. I have just given a practical example of what don't care is. Okay, so whenever there is a function, so for this particular arbitrary function, we said this particular input combination is not possible. So in a practical circuit like this, there are only four different possible combinations is available. Rest of the four combinations is not possible. So when I am going to make a truth table, I am going to write don't care for these four other combinations. I am going to write only possible combinations as 4, and from these I have to make an 2-bit. So this is just an example of ADC. So don't go to. I am just giving you so that in the back of the mind you know where these don't cares are coming. Similarly, many a times the computer does some computation and the final output it will give in BCD format. Okay, and once the why we need an output in the BCD format is to drive a 7-segment display. Now if you see here, this is an IC which converts this. We require a 4-bit information to drive to represent 0 to 9 values, right? 0 to 9, and then depending on what is, if it is 0 0 0 all here, it will be 0 here. If it is a 1 0 0 1, that corresponds to 9, it will be 9. So there is so when we design this particular IC, okay, what are the possible inputs? It is 0 to 9. But we are not going to design this circuit thinking we will get an input of 10, 11, 12, 13, 14, because that will complicate my circuit. So from 10 to 15, for the 10 to 15 and min terms, I will take it as don't care. I will not take it either as 0 or 1. I will take it as don't care, so that the design of this IC is simple. Is the concept of don't care clear to all of you? Yeah, anybody? See, you can ask me. I can keep explaining it on a n number of times. Only then you will understand things properly. Mariam, is it okay? Is it clear to you? At least don't care. Where do we get this don't care from? Yeah. Okay. So what we will do is now we will take an 10 minutes break here. It's 57. So on my computer, so 14:57. So 15:07 we will start the class, and then we will have a half an hour session where we will take a few more examples of 4 variable KMaps. Till now we learned how to do about 2 variable and 3 variable. We will just expand this concept to 4 variable, and also we will see some don't care conditions in 4 variable. So with that you will come to an end of the KMaps. Okay, it's a pretty simple technique which you can use in your day-to-day if you have to design some circuits with up to 4 variables, and in fact up to for 4 to 5 variables, and a KMap is pretty easy for you to do. So this technique, and we will up to 4 variables we will see today. Okay, thanks a lot. Take a break now. It's 58, so 10 minutes from now. Okay, thanks a lot.